Okay, we continue to talk about next lecture about supportive vector machine. Okay. So different from the LDA and the PCA, SVM is a reproject to higher dimension based on the kernel function. The kernel function is the activation function, the same as deep learning. So the purpose for SVM is this way. I'll show you. We want to find a discrimination line to separate both classes. However, in reality, okay, they will overlap. So they will cause some error for the discrimination line. So if the distribution is like this way, and the linear discrimination line, LDA cannot solve this problem. Okay, because we need to find a line is curve, higher dimension, okay, to separate both classes. So SVM, the solution is this one. Based on the activation function, but here we call kernel function, we will project the original, project the samples from the original space, project to higher dimension we call feature space. In the higher dimension, we can use linear discrimination to separate both classes as SVM. Okay. So the purpose we try to find this one, the kernel function. So back to, so before we talk about this one, the same, I will teach you the linear algebra about the line. The line, this is a line, okay? So this line, it intercept with x1, they have a distance q, p. Intercept with x2, well, q. So this line equation become this one. Okay, but you don't need to worry about p and q. So just that you know, okay. So the equation like this one. This line equation looks like this one. And we try to reorganize this one become qx1 plus this one, qx1 plus px2 plus or minus the constant term. Constant is shift, okay? And we use a vector format, the inner product format. So this is a samples, this is the parameters. Okay, so this one is a rotation vector. This is a constant term. So finally, this equation, the same or equal to wx plus b. So the same as LDA. 啊，这是让你知道说 ，OK， 这物理意义是什么？就从这样过来。So W is a rotation, B is a translation. Continue to talk about this one. So here we try to show you is W and X. This one. We want to show you this term. So this term, actually this way. We have a L here. The normal direction, W will pass through the 0, 0. Okay, so the same. W is here. This W. This L. So W control the rotation. Okay, and if you fix the rotation, and L will be to shift this translation. So the same. So here they try to explain to you. Use the other way to explain to you. Okay. So suppose in this L, we have 2 points, XA and XB. So any point you input to this L will become 0. So XA input to XA will become, the equation will become 0. Input XB become 0. And if we subtract both terms, the constant will be gone to the male constant. So we become this one. So what's the meaning for this one? This meaning is this line, XA and XB is along the same line. So 2 points is a vector. So this one vector here. So this vector will orthogonal to W. Orthogonal meaning 90 degrees. The inner product be equal to 0. This is try to tell you this way. So W is they tell you. So W is a normal vector of linear equation. They just try to prove this way. 它只是证明说，那 W 跟 X 垂直嘛，那垂直就是什么？内积等于0。那内积等于0，那垂直意思是说我一条线上面取2点，两点在同一条线上嘛，那2点就产生一个什么向量？这里会有一个向量，那这个向量跟 W 向量内积等于0，代表这是90度，是这样。它是证明这件事情。好，那我们继续。这里要讲什么？这 one tell you is what's the B? We talk about W. Here we talk about W. W is rotation. And then we talk about B. So what's the B in this equation? B is translation. It's meaning the distance from 0, 0 to W. That's B. Oh, sorry, that's not B. That's this distance. And if B equal to 0, it's meaning this line will pass through the 0, 0. 我刚刚讲错了哈，这个距离不是 B 啊，这距离是 D， 到时候我们到下一页再讲。啊，只是跟你讲 B control the distance from 0, 0 to this line. So B is shift. So when B equal to 0, meaning this line pass through the 0, 0, 就这条线 orange. 好，我们再继续。And then I want to teach you about inner product 内积嘛，你们学过内积的东西。那内积代表什么 ？What's the meaning for the inner product? So if two vector, this vector A and vector B, so A inner product B is equal to what? Equal to this equation. What's this equation? It's the relationship between two vectors. The inner product A and the B, the physical meaning is what? The physical meaning is the relationship between two vectors. 它的相关性 The relationship meaning the similarity. 相似度 Okay. So A inner product B equal to what? Equal to this the magnitude 是大小 A and the magnitude B. And then what's cosine theta meaning? Cosine theta meaning the similarity because theta, if theta equal to 0, that's meaning this theta equal to 0 is meaning the overlap. So meaning the same. If theta is bigger, so A project to B will become smaller. Okay, so this way. 这你们大概知道，但我还是讲一下。这个角度嘛，那这个如果越小 ，theta smaller, so it means A project to B and they have a strong correlation. If theta is bigger, even though 90 degree, if they are 90 degree, the projection equal to 0. There's no relationship. So the cosine theta is what? Is the correlation between vector A and the vector B. So here, cosine theta equal to this term. What is this term? Cosine theta equal to A. Oops. Sorry. It's A. Inner product B. So what is this one? Okay. So what is this one? This one is a normalized cross correlation. This is normalized cross correlation. This univector A and univector V is the inner product of this one. So cosine theta, actually, this is between 1, 0, and minus 1 to 1. Okay, but if I do absolute, 假如用绝对值的话，那就 between 0 and 1. So this is a we call normalized cross correlation 就这里。So cosine theta is the NCC, the relationship between two vector, univector. Okay, and what is this one? Because absolute, what's the physical meaning of absolute? Absolute meaning the magnitude 大小，绝对值代表距离，代表大小，所以这是 A 的大小 ，magnitude of A，magnitude of A this one，magnitude of this one project on cosine theta project on B, so this one is the distance here, projection distance. So A cosine theta meaning the vector A project on this B direction. So cosine A project on B actually equal to this one. So that's meaning original vector A, what's the component 它的分量 along the B direction. I say again, you have a vector A and you have magnitude for the magnitude for A, 就 A 的大小 project on B, 这是投影量 projection weight is this one. 投影量 equal to the A vector, the component along the B univector B direction. Projection meaning 你的向量 A 在 B 方向的投影量，所以这两个是一样的，教你这件事情。那我们继续。So, what's the distance from zero origin to the line? The D, the distance D. How can you count D? 一个点到一个线的距离 D 嘛？那 D 是什么 ？D 的距离是什么 ？D 的距离是你有一点 x 在线上 ，you have one. What's the D? D is here. D is meaning any point along the line project on W direction. D is meaning any point x along the line project on the W direction. So this one, D equal to any point x project on the unit vector of W is in W direction. So this one equal to this one. Okay. 这个 D. So we define the D. Okay. And then again, based on this one, we want to based on this one. So original equation 9 is here. Equation in this one. Okay. So we in the denominator we have a normalization term. This normalization term. So this equation become this one. So we got this term, and you will find out this term is equal to D. 再讲一遍哦。What's D? D is distance from 0, 0 to this 9. So the equation become, the result become this one. 那我们把这个带入式子里面去，我们要找到这个。为了找到这个，所以我们把这个式子重新组合一下，就变成这个式子。就这式子就变成这个，所以这个就变成 B 啊，这两个就 so the result here 我们就得到这个式子。可以哈。所以意思是说 ，what's the meaning here for this one? We just prove this one. It's meaning any point 0, 0 to this 9, the distance D actually is the constant term, but you need to do what? You need to do the normalization this term. B 嘛，那除以它的这个那个 normalization term W， 因为你要找是 B 这沿着这个 W 方向的分量，这样子，可以哈。好，那我们再继续。So our purpose is that the distance. There's a point to distance. Right now, we want to find the distance between 2, 9. What's the distance between 2, 9? D. Why we want to find this one? Because here, if for a discrimination is a 9, we separated both clusters. That's for the discrimination 9. However, if we can find 2 9s and the 2, 9, if this distance between 2, 9 is wider, that's meaning the 2 clusters we can be separate as aware as possible. It's not only this original dash is original discrimination. However, if we can find, we call margin, this one, margin. If we can find a margin, and this margin can separate 2 clusters or classes as aware as possible, and then this answer will be the best. And this one, the margin right now is the best method for face recognition using deep learning. Right now, the best deep learning for face recognition, they include the margins this term. Okay, so what's the margin? It's meaning not only original we have a line, dash line here. That's the equation L. However, we try to find given margin. We hope this margin, the distance between 2 margins, 2D. We hope this margin is as bigger as possible in order to separate 2 classes. That's our purpose for SVM. SVM 的目的 就是不只是把这找一条线把它分开不够。为什么 ？Because your training data and the test data are different. SVM is a supervised learning， 是监督式的，是要去 label 它的。So when you collect data, okay, you try to find the discrimination line using SVM and try to separate both classes. That's not good enough. We try to find a bigger margin to separate both classes. That'll be better. So margin is important for the discrimination. In order to define the margin, you find there are two lines here. 是两条线哦 ，margin 是两条线。Okay. Now, right now, the best face recognition method using deep learning, they include in the loss function. In the loss function, they include margin. Right now, what we talk about discrimination or SVM, actually we talk about loss function. 我们现在讲这些都是跟 loss function 有关。好，那我们再回到这一边。好，所以我们现在目的就是希望we are purpose try to find this one, the distance between two lines, the margin will be bigger as possible. That's meaning we hope DS2 is bigger. Okay, so what we try to do is this way. For the equation L1, we have a constant B1. So the distance from 0, 0 to this L1 will be here. Will be B divided by W. For D2, for the other line, will be B2 divided by W. So both are the distance from 0, 0 to L1 and L2. Okay. And our purpose is to try to find DS, the distance between two lines. So it will be D1 minus D2 and equal to this one. So finally, we get this result. This is important. Okay, we continue. We already talked about this one. We keep this one. 你先记得这个，这个会待会用到，这个会用到。We will remember keep this one. We will use this one very soon. Around let me check. Here we will use. We'll continue to talk about this one, but here, this turn, we will continue to improve this turn. So finally, we will get the result is here, this one. Margin 2D is this one. So we back to here. We continue here. And this is a class, the classes. So if this is a line, right? And if the class 2 will in this side, class 2, and you put any x1, x2, you'll become bigger one. So if class 2, this any value are bigger than 0. Sorry. In class 1, any value put into the xi or smaller than 0, 0. It's two classes. So we continue. Okay. And here, we back to here. We try to find the bigger margin. So suppose this distance is 2D1. D is small one, and 2 double, 2D1 is 2D2. And so this result is better than this result. See, this is a line, sorry, a W, normal direction W, and this is a line. So this is rotation. So the same as LDA. So we try to find the best W. The best W can have the bigger margin here. Okay. So we back to here. So we have a Wx plus b equal to 0 is a dash line. Okay. Ws plus b equal to a is one line. Minus a is the other line. So we have three lines. One is the dash line is 0, plus b is a dash line, and the other because constant term is shift. So one is equal to a, the other one is minus a. Okay, because they are constant, so each term we can divide it by a, so become b prime, w prime, b prime, w prime。因为 a 是一个scaling term， 是一个常数项，所以我把常数项都除以 a 的话，就变成1跟负1，那就这常数项都除，那不会影响到，因为我是一条线嘛，那线跟常数项没什么关系，只是 normalize 的常数项，所以我就保持这个。好，那我们再继续。那你就会发现，这个常数项这 scaling term 没什么意思，你可以是1，可以是 k， 这都可以。只是跟你讲说，那这个就叫我们定义这个叫 margin。我们定义这个叫 margin。现在是最主要定义这个 margin 这样子。好，我们再继续。好，那这才是重点开始，就是说 ，OK， 那我们刚刚讲不是除以变成1嘛，跟负1嘛，所以 this equation, this margin line, this one become plus 1, 0, minus 1. So the line we divided by the constant term, so this will become this original one plus b become 0. This one margin line become 1. This is ds, and d1 is 0 to first line, d2 is 0 to the second line. So this is the margin, and the margin will become this one, okay? And b, this one is b minus 1, the other b plus 1, this one, b minus 1, b plus 1. So finally, you'll find out actually the distance between two lines will become this one. So that's important. 你最后发现这个低距离会变成这个结果。两条平行线，这个 L 的平行线，最后变成这两个平行线的距离啊，这 margin 的距离就是变成这样，就是2嘛，两个单位 along W, 2 unit along the W vector. The margin, right now we don't know the W because we try to find W. So right now we don't know W, okay? But the margin, you'll find out the margin is the distance between two lines. And this margin actually is a distance, it will become 2 along the W direction. 这是最后结果。好，那我们再继续。So our purpose, okay, this one equal to this one. 相是距离嘛。So our purpose is what? Try to maximize this one. Our purpose is try to maximize the margin. 你希望 margin 越大越好。So we want to maximize this one. And maximize this one equal to minimize the denominator term. So actually you try to minimize this term. So your formulation, your equation become this one, W. But what's a half? 2分之一是代表什么？ This just scaling term. Doesn't mean anything. That's equal to the exponential term of the Gaussian distribution. The Gaussian distribution, the exponential term has a half times 1 square. So this one is later if you do that because it's 2, this square, this 2 order 2. If you do derivative, will become this deleted. 而这 NG 没有什么意思，就是 constant term. So this become our loss function. This become our loss function. However, it's not enough because we are doing classification. So we have some constraint. So this is our constraint. That's meaning what? Meaning here. So our loss function is we try to find the maximum margin here. So that's this way. We will try to find maximum margin. However, try to find maximum margin meaning minimize the W. Minimize that's a normalization term. But it's not enough. Our constraint is classification. So that's meaning we try to, the constraint is this one, this 9. So this 9 is here. So when class 1, y is equal to, y is the labeling. We do the labeling. So if y become 1, and this is a 9, so 1 times, so that's this way. Sorry. This one. This is the equation. So when the equation, this class 2 is meaning the result bigger than 0, but here label 1. Here label -1. Not 0. The labeling class is 1. This is -1. Okay. So when like this equation, if any sample belong to class 2 is meaning the label 1 times this equation and this side and become bigger than 0. If the class become class 1, is meaning the label is -1 times this one. So the same, minus equal to positive, so become bigger than 0. So the constraint will become, sorry, this constraint become this one. 就是说你的一边是大于0嘛，那你大于0是 label 1，所以1乘上大于0就大于1。另外一边是小于1，就是负1，那负1乘上小于1就负嘛，负得正，就变成也是大于1。So this become the constraint. So this is your loss function with constraint. 这样子，可以哈。好，那我们再继续。Now we will solve this one very soon. We will solve this one. So this is our first constraint. And we will optimize this one, try to solve W. Okay. But here, the problem is what? Here, problem is this way. This is a low dimension. Actually, the distribution is like this one. So that's meaning what? Meaning your margin, you have margin here. 你要找一个，这变成一个 margin 在这里，这样。we have a margin, right? But in reality, 在我们实际上 in reality， 我们实际上是要找变成，因为 original this is dash, right? This one. This original distribution, we hope. So we have the margin here. But in reality, our distribution like this way. I say again, original distribution like this way. That's a theory. 理论上是这样子，我们去找一个 margin 嘛。In theory, 在理论上是这样。But in reality, in practical, the distribution will like this way. In this way, it's not easy to find a linear discrimination. 你在实际上这种分布的话，你很难找到一条直线来分两个嘛。 你要找到一个是曲线来才把它分嘛。那曲线就 margin 的曲线。So SVM has two concepts. One concept is a margin. The second concept is in the low dimension, we cannot use linear discrimination. So they will try to find a kernel function, activation function, to project each point to higher dimension. In higher dimension, they can do the margin. 他们在高纬度在做 margin 是这样子。So that's the total concept for the SVM. 我再讲一遍 ，SVM 是理论上它要引入 margin 嘛，但是这个 margin 在低纬度的话，你还是没办法把这种自然界的这种分布区分开来，所以你一定要投影到高纬度，才有办法在高纬度用线性的方式把这两个 class 分开，这样子。所以刚刚有介绍你们 margin 的观念，那现在要介绍你们是这个 kernel function， so this is a kernel function here。所以 continue， 那是高纬度，这10个纬度。你本来 x 变成这样子，你本来就 x 嘛，现在1 2 3 4 5 6 7 9 8 10 so this dimension original is 3 dimension 3个纬度 right now you need to use 10 dimension project to 10 dimension 的纬度这样子。好，再继续。那一样 can you discriminate this one? No, in linear discrimination you cannot do this one. You need to project to this 1D. You need to project to 2D, so the distribution becomes this one. So you can use linear discrimination to separate two classes. This one example to tell you original distribution like this way. In 1D, you need to use curve, high dimension to separate, to classify two classes. But in the other ways, you can project, use kernel function, project to higher dimension, this curve. In higher 2 degree dimension, you can use linear discrimination to separate two classes. Okay, so SVM is we try to use kernel function to project to higher dimension. Okay, so this kernel function. Okay, so the kernel function, they introduce you. One is a polynomial, the other is the Gaussian distribution. The third one is sigmoid. Those are activation function, also the kernel function to project from lower dimension to higher dimension. 还有帮你介绍，不止这几个，还有几个，但是这也是简单跟你介绍有 polynomial， 就都那个高纬度的嘛，多项式，一个是用高循的，一个是用 sigmoid 的这样子，啊 ，tangent h 这样子，好，这跟你讲一下而已。好，那这样的话，你在高纬度就可以做这件事情。所以我们现在两件 right now we introduce two. One is margin, the other is a kernel function. Okay. The third one is to avoid overfitting problems. So we will introduce allow some error. 就是说，对不起，刚刚讲的有三个东西哦 ，supportive vector machine 有3个东西要介绍给你，所以跟 deep learning 有关。那刚刚讲到一个是 margin， 第二个是那个 activation function， 那第三个是什么？不能 overfit。那不能 overfitting 是什么？不能太完美。training data 不能太完美。好 ，you cannot be perfect for the training data. You should allow some training error. So they allow some error. So originally the margin is 1 is 2, but right now you will allow some error term. Actually, the error term is kind of a noise. So that's meaning your loss function will need to consider one is the margin. Okay, the second is activation function. The third one is the noise. I say again, when loss function, the perfect loss function, need to consider is the margin. Okay, the second is the kernel, the activation function. The third one is the noise. Noise is meaning allow some error to avoid the overfitting. Okay. So because we allow the error, so this term will reduce. Original margin is 1. Right now will become smaller, so we'll minus this one. That's meaning this margin will become smaller. 你要允许一些错误的东西，是 distance 啊，所以我们要允许这个 margin 就变成有这个 error 的 term 这样子。好，那这样 ，so the final loss function will be this one. This is your final loss function for supportive vector machine. Okay. So your final is first of all, you allow some noise, allow some error. Because this loss function, so you have some error, so you include error term here. Okay, so this is also error term. Okay, you allow some margin, so margin is this one. 你用这个式子当有 margin 的东西，这个 so error term 跟原来的 margin， 这两个都有了。好，那少一个什么？你少一个 activation function. So that here, the final one, you don't have an activation function. So we will include activation function to here. 我要讲一遍，我们现在变成有 this one, you include some error term. You also have a margin. The last one is that we want to include, this is low dimension. X is low dimension. You want to be higher dimension. So this one become activation function. So this is your final equation, final loss function. 是这个这样子。So this is a complete SVM. 这样可以哦 SVM. Now, so you are back to think about your deep learning. Right now, your deep learning use mean square error or cross entropy, right? And then you do not have a margin. First of all, you do not have a noise term. Okay, so you think about, and right now you have activation. You already have an activation function because activation function is already inside a network. So you have an activation function, but for the final one, what kind of activation function you want to use? So for loss function, okay, what kind of activation function you will use is one issue. Whether you have a margin, whether you have a noise. So this one. Okay. So we want to optimize this one. So they optimize this one using Lagrange. 我找一下哈 ，Lagrange 在哪边 ？OK。Oh, this one. They use Lagrange to solve above equation, 就这个 term. Because your noise term, so they use Lagrange. So Lagrange is actually similar to the gradient descent iteration to the derivative. When you solve gradient descent, any unknown parameters, you try to derivative. The same for the Lagrange, you have one more noise term. So you just try to solve this Lagrange. See, you just use derivative. So the same as gradient descent. So that's it for the SVM. 我这里就没有再解了，因为它就是从这里开始解下来的啊，所以 SVM 有点复杂啊。对，这还有一个 waiting 我还没讲。OK， 我把整个讲完，我再下课了哈，把这个快讲完了。好，那我这里在最后一个 我们讲到三点了，那3点的话，就是用 Lagrange 来解这个未知嘛啊，所以可以 Lagrange。And final one, 4 points. The final contribution for SVM is that we have for each margin, we call support. Why we call supported? It's meaning important sample will give him the weight. If not important sample, we don't need to care about that one. So it's kind of an imbalance, kind of a prior probability. Okay. So the last one is what I call supported. It's meaning any points will affect our this 9. That's called important feature. Important feature, I'll give him a weight. So the weight alpha will be bigger. If they are not important samples, I just ignore it. Because those are not what I mean not important is meaning it's far away from the discrimination one. So those features is easy to discriminate. So what I try to care is easy confuse. That's called hard examples. Hard samples. So hard, HARD, hard sample, you will give him the higher weight. Okay, so that's the alpha. So if this sample is important, X, I'll give him large alpha. But alpha you don't know, you want to evaluate. Okay, so based on the equation, see your equation have one more alpha term. This is the original, right? Original one. Okay, but right now you want to do the weighting for each sample, so you will become this one. This is your Lagrange function, but for each sample you want to give him alpha. That means the weight. So you also need to solve alpha. So after you solve alpha, you will find out the sample close to the bound margin, the weight will be higher. So the equation, our equation become this one. Okay. So we will include the margin, we'll include the supported weight, we'll include activation function, we'll include the noise term as SVM. OK， 好，那我大概讲，这是概念了。我现在只能，因为 SVM 本身是一门学问，好，一个学问。那我现在只讲概念的问题。那 SVM is actually is a loss function， loss function。所以我再讲一遍 ，SVM 它有几个重要的，一个是你要有 margin 的观念嘛，那 activation 的观念嘛 ，activation， 然后 margin 的观念，对不对？好，然后再来就是你要在最后你要加上一个 weighting 的观念，就每个 sample weighting 的观念这样子。OK， 那这些东西变成 Lagrange 的东西，那 Lagrange 东西你要解它，就用 gradient descent 方式来解了。You want to solve Lagrange equation, use gradient descent. So this is the same as the loss function in the deep learning， 是一样的。OK， so that's for the SVM. We will take a break.